This is the world's longest, shortest introduction to Bayes networks. We have done 4 classes and we are going back to Bayes learning today. To recap what we have done till now, we talked about Bayes networks, we talked about how to specify them, we talked about inference over them using Markov chain Monte Carlo or Gibbs sampling methods, for example. And then we talked about learning Bayes networks, and we started with the idea of pure Bayesian learning, where you essentially assume that there's a prior over the hypothesis, and then at which point then there is no difference between learning and inference. All you do is, as new examples are coming in, then you essentially compute the posterior over the hypothesis space. Okay, and that would tell you what hypotheses are more likely and what hypotheses are less likely, having seen the data. Okay, you had some idea about what might be more likely versus less likely hypothesis before, and having seen the data, you now keep changing your mind as to which are more likely, which are less likely. Hopefully, if the data is essentially unambiguously telling you about the primacy of one particular hypothesis, then the distribution becomes more and more and more peaked. Okay, and then either way, in terms of prediction, all you do in Bayes learning basically is you are predicting the next data point given all the data you have seen till now, and you do that by essentially considering what is the probability that there is a hypothesis H1 is true, that you will get it from the posterior of the hypothesis space, times what's the probability that the data D will be produced if hypothesis H1 is true. Okay, so in essence, you would do, you have probability of H given data D. This is the posterior, and then what you're trying to do is to predict the next data point Dn. Then you are essentially trying to say what's the probability of the next data Dn given. So what's the probability of next data Dn, next data being Dn? Okay, that's equal to probability that will be Dn given H1 times probability H1 given D. Okay, and now you have to do this over all the edges. So essentially I can just say I write integration now. Earlier on I wrote summation. Okay, if you have a discrete space of hypotheses, you just have to sum over all the hypotheses what each of the hypotheses are giving as the probability of the next data being D1. Okay, if you have a continuum of hypotheses, you have to do integration. Okay, so we started with the Bayes learning, and actually we in fact used the summation version and still said, well, actually it's just too painful to keep track of all the hypotheses, and then so instead what we would do is we will realize that you can take the summation or the integration and then say, well, this is approximately equal to the H max for which this term becomes the maximum. If you're doing a sum of many things, then that sum can be approximated as the largest term in the sum. And that would be fine if everybody else has close to 0 probability anyway. Okay, and so for H max, then then if you do that, okay, that is the map based on the maximum and posteriori learning, and then we further simplified that to maximum likelihood estimation, where you even ignore the prior over hypothesis. Okay, so that's what we have done, and then we talked about how to do learning maximum likelihood estimate based learning for Bayes network parameters. And then we also talked about how you can use the same thing to learn Bayes network parameters when the data is not complete. That's the expectation maximization algorithm. Okay, and then we finally also talked about, actually I think before EM we talked about if you have the complete data, how to learn the topology of the network. And there we actually pointed out that if you just keep adding basically links to the topology, that's not going to work very well. Because essentially a complete Bayes network will always maximize the likelihood of the data. So that means you'll always overfit your network to the data. Okay? So instead you need to somehow penalize the networks that have too many links. Okay? And by doing that, in essence, we are already going towards Bayes learning. Because if you penalize network in terms of their complexity, that means you have some sort of an idea as to which hypotheses are more likely versus less likely before you ever set your eyes on the data. Okay, again, this is like the biggest difference between Bayes learning and normal frequentist statistics. Frequentist statistics basically says, essentially, I have no idea there is no prior on the hypothesis. I'll just look at what data tells me. I have no preconceived notions. Okay, Bayes learning essentially says you always have some preconceived notions. Okay, if you think everything is equally likely, just put a uniform prior. If you think some things are more likely than other things, you put a peaked prior. But then that is basically, so again the idea is that's called bias in some sense, and in fact learning is impossible if you don't have biases. Okay, because there's just too many hypotheses, and you essentially have to have some prior or which hypotheses are more likely and which are less likely. And that's what the prior hypothesis prior tells. Okay, so in looking at the structured learning, we already started seeing the slow cracking of the maximum likelihood estimation based learning methods. Okay, so now we'll come back fully to Bayes learning. Okay, except we'll now see Bayes learning in the scenario where the hypothesis space doesn't have to be discrete, it can be continuous. So what I'm doing today is essentially the same candy example. Remember the candy example? Earlier on, we made the hypothesis space discrete by artificially assuming that there only were 5 different hypotheses possible. What were those 5 different hypotheses? 100% cherry, 100% lime, 75%, 25%, 25%, 70%, 50-50. Those were the only 5 possible. But really, that basically means somebody came and told you that those are the only kinds of bags possible. A more general scenario is that you actually think the hypothesis is theta. That means theta fraction are cherries and 1 minus theta fraction are limes. Do you see what I'm saying? If you do that, then theta becomes a continuous quantity. And so instead of summation, we will start doing integrations. Okay, so we'll get back to Bayes learning through that form. So essentially all I'm discussing today is sort of parallel to the very first discussion of Bayes learning. Okay, and all the reasons we got away from Bayes learning last time around still hold this time too. Okay, it is actually a pretty hard thing to handle to do these kinds of integrals, because you're essentially considering computing the posterior as the data is coming in can be quite hard. But in some scenarios, it might be easy enough. Okay, and there is reason why you want to go back to Bayes learning, because that's the right thing to do in essence. Because that way you don't ever have to make up your mind arbitrarily. Okay, so that's basically what I'm going to do today. And everything here can be seen as required to understand LDA. Although LDA is not somehow the golden, it's not just somehow the, what's the thing called, the holy grail of this entire discussion. It is an example of the kind of work that is being, that you would like to understand. And to understand it, you need to understand everything else I've just talked to you till now, as well as half of today's class. Okay, and the second half of today's class, we'll start talking about text models, which is applying statistical model to text, and then LDA is a particular kind of statistical model for text. And then when using that statistical model, you will see, oh yeah, thank goodness I know Bayes networks. Thank goodness I know how to do EM. Thank goodness I know what is the difference between Bayesian learning and non-Bayesian learning. Thank goodness I know what is Gibbs sampling and what is, how to use Gibbs sampling to do parameters to inference. Okay, so that's the whole thing. So, in fact, one of the other things I'm hoping to do, in fact, I forgot to do this. Actually, let me just see if I can. In fact, I wanted to put two things, and neither of them might. Yeah. So this was on the front page over the Thanksgiving weekend. Scientists see promise in deep learning programs on New York Times. Of course, none of you read New York Times. None of you actually see real papers, but if you saw it, you would have in the front page. But it's and this guy is Jeff Hinton, and he talks about deep belief nets, which are multi-layer neural networks with probabilistic semantics. And one of the other things I want to do, even though I made as an LDA, is one of the holy grails, for going through all this. I also want to actually explain to you that with knowing what you know, you can also understand essentially deep belief networks. Okay, so that sort of tells you that whatever we taught, instead of one class, I took more or less 4.5 classes. But I believe that's kind of important if you don't know Bayes networks before, because you need this background to understand this article too. And this is it's on the New York Times, so presumably it must be useful stuff to know for you, and you can actually know this from what you're doing. Okay. So back to Bayesian learning. So now I'm going to start having started from the Bayes learning and then going, running away from it because it's too hard and doing maximum likelihood estimate. Now I go back to Bayes learning, saying sometimes the maximum likelihood estimate doesn't tell you what's the right thing to do. Okay, and the question, of course, is the following. So suppose I have told you that I'm just tossing a coin, okay, and I tossed it twice, and it came heads twice. What is the maximum likelihood probability of getting heads with this coin? What?
It's 100%.
100%. 1. What's the maximum likelihood probability of getting tails? 0. That's what MLE will tell you. Okay, and maybe you'll say, well, nobody will actually take zeros, so maybe I will fudge it so that whenever there are zeros, I'll make it at least a small number. I understand that. Instead of saying 1 and 0, you'll make it 0.99 and 0.01, and you can feel happy. Okay, but more interesting question, of course, is suppose I actually have 3 tosses and 2 heads and 1 tail. Now, what do you think is the probability, maximum likelihood estimate probabilities? It's 0.75 and 0.25. I would argue that that's just as bad as the 1 and 0. It's just that 0 is forever, so if you actually ever think any particular probability is 0, then you're in big trouble later on. But basically 0.75, 0.25 is just as bad. Okay, now I'm bringing out right now some currency notes from my purse. Okay, I just looked at it. The first one is a $20 bill. The second one is also a $20 bill. Okay, the third one is a $100 bill. Okay, what's the probability that the next bill will be a $20 bill? You would be pretty happy to think it's 0.66 because you have no clue what kind of money I have in this purse. You have no preconceived notions unless you think professors are either fat cats or really poor people. You have no preconceived notions, and you don't quite know. Well, looks like the data tells what the data tells. So you're not as worried about going with 0.66. Oh, by the way, in the 2 heads, 1 tail, it should have been 2/3, 1/3 instead of 3/4, 1/4. Obviously, very mistake there. Okay, so it's the same thing. So you are more worried about saying 2/3 probability heads, 1/3 probability tails for coins. But you have no problem in saying 2/3 probability that next one will be $20 note and 1/3 probability that the next one will be $100 note. Because you probably have no clue as to, you have no prior over what kind of money I have here. Do you understand what I'm saying? Okay, so in general, MLE kind of assumes that you have no prior at all. And so the data tells you everything, which is completely fine if you have a large amount of data. But if you just have a few samples of the data, if you have just few training samples, then MLE estimates can be pretty bad, as we just saw here. Okay, so in fact, in this particular example, what we are doing is playing the game with tossing of the coin versus thumbtack. So, tossing of the coin, everybody has priors. They think there's a strong prior that it's half and half is the heads and tails probability. Thumbtack, unless you have played with thumbtacks, you don't quite know whether, if it comes like this, it's called heads. If it comes the other way around, that means it sits with the pointy thing pointing up, then let's call it tails. Okay, you may not have as good a prior. So you're probably more willing to go by the data here and less willing to just go by the data here, especially when the data is small. So in general, the point of this whole argument is that you tend to have background knowledge about the problem beyond the data. And you would like to bring that into the decision making. Yes?
So it seems like you're kind of self-defeats because if your priors are really, they're really solid, I guess you could say, then you would need a lot of data to change those preconceived notions. And if you were to go the other route, you just need a bunch of data anyway. It seems like you just need
Yes, you're right. But here are two issues. One, of course, is, again, I'm fond of saying that if anybody tells me you are prejudiced or you're biased, I say thank you. Because if me and my ancestors were not biased and prejudiced and did not learn from a single example, the first tiger eats my friend, I think, oh, that's just the first tiger. Maybe the second tiger would do something different. Do you see what I'm saying? I had to jump to conclusions with small amounts of data. It's not like I had 10 million tigers eating people episodes from which I learned without doubt that tigers eat people. So if you see a tiger, run. Do you see what I'm saying? I had to jump to conclusions. Okay, you are very much true. You're very much right that having prior knowledge can be called being wise or also being called prejudiced. You see what I'm saying? And this is an issue, and computationally, if you have prior knowledge and you don't use it, you are essentially just putting your hands behind your back. Okay, but as long as your learning algorithm is such that it is able to let the prior be overridden by the data, then that's fine. So people can have biases. I can very well come into this world thinking that people with long hair cannot do math. There's nothing wrong with it whatsoever, in my view. But if after seeing 8 people with really long hair doing, highfalutin integrals, if I still think, oh no, those are all just experimental errors, I will still stick with my my hypothesis, then I have a trouble, because I'm not doing learning. Okay? So, and then Bayesians also basically say, your prior can just say everything is equally likely. That could be sort of a not having too much purpose. The important thing is to allow for prior over the hypothesis to be specified. And it turns out that changes everything in many different ways, because you no longer have this differentiation between inference and learning. It's all inference. And we talked about it before, I'm going to re-talk about it. Because at this time I'm going to talk about it with hypothesis space possibly being continuous, because that's what winds up being useful for the LDA sorts of models. Okay, So this is basically, the point of going back to base learning. Now, here is the interesting thing. I mean, we knew about it last time too. The tricky part, of course, is, so suppose I'm doing heads, the coin toss experiment. Okay, suppose I'm thinking that let theta be the probability that the coin comes heads. Okay, MLE just tries to figure out what the best value for theta is. Okay, Bayesian learning says I need a prior over theta. Okay, now this is the prior over probabilities. Now that's the good thing about Bayesians. They can, it's like I think there was this, they can put a distribution over everything. This is prior over theta is distribution over distributions. Do you see that? Okay. So you are saying, I don't, theta itself is the distribution with respect to which heads or tails will come. Now what that theta is, whether it's 0.5 or 0.1 or 0.2, is being given by a prior over theta. Okay, for our discrete example, that prior basically was, I think I made it as 25, 25 and something. I mean, I put for all those 5, I put some percentages such that everything adds up to 100. That was my prior. Okay, so here also I should be able to provide a prior. The only interesting thing, of course, is the hypothesis prior now is a continuous distribution, not a discrete distribution, but a continuous distribution. And there it was easy to think in terms of just 5 possibilities and keeping track of the distribution over those 5 quantities. Here it's an actual, continuous distribution. Okay, and so if I do have this prior p theta, then starting with the prior theta, we just need to compute the posterior over the hypothesis using that old expression. Okay, and once I compute the posterior over hypothesis, I can the prediction problem becomes that integral. Okay, and everything is essentially inference. Everything is just using the Bayes network to predict. Okay, now the one challenge that we almost did not even think about last time, and it becomes important, is we want to be, so suppose I found out, suppose I carefully put, let's say, a particular prior on theta. Let's say Poisson prior. Okay, then what happens, I see some number of heads and tails coming. So now I have to compute the posterior. Okay, now if I have a Poisson prior, after seeing some number of heads and tails, am I guaranteed that the posterior, I know that the posterior will be a different distribution, but the question is, would it still be a Poisson distribution? Do you understand this? Okay, so the idea is, ultimately, that, let's say, the probability of the prior over the hypothesis space is written as some sort of a Poisson distribution. It's a particular distribution over discrete quantities. Okay? No, actually, in fact, it should be continuous. Let's just do it normal. Normal distribution. Okay? Now the question is, if after seeing some number of heads and tails, I will have a posterior distribution. My question is that posterior going to be in the same form as the prior? In general, no. In general, no. Okay, before I go any forward, I want to ask you this question. Why didn't we care about this before? I made a big deal about it right now, right? Is the posterior going to be in the same form as prior? In general, no. And so, if I were to give you a prior that will keep the same form when you go to the posterior, you would be happy. Okay, but before you can understand how great a deal it is, you need to understand why is it a big deal to begin with. So why did we not care about this issue of prior and posterior being in the same form when we did the candy example?
It was discrete space.
Distribution?
Yeah?
It was a discrete distribution and we couldn't compute all the values individually.
So basically, not just discrete, it's a non-parameterized discrete distribution. It's a non-parameterized discrete distribution. So it's like the machine language of the distributions. You essentially said, for this value, this is the probability. This value, this is the probability. This value, this is the probability. And if it's a discrete variable, however many number of values that variable takes, you need to provide a probability for each of them. And when you go from one level to other level, that value doesn't change. Okay, now here, think about the following example. Okay, if you start with a value function for MDP, big whiplash, going back to MDPs, okay? Start with a value function for MDP. You did update on the value function. Will the value function size increase?
No.
Why won't it increase? Because you thought when I just said value function, you assumed that value function was written extensionally as a big old table. Every state's value. Do you understand what I'm saying? Okay? And so clearly you are sunk already. You represented the value function with the largest amount of space anybody would ever need to represent a silly value function. So of course when you update the value function, you will still be of the same size. Suppose, however, you are actually representing your value function in some factored form, like a decision diagram. A simple decision diagram. Algebraic decision diagram. And the initial value function is a little, very small algebraic decision diagram. You look at it and you marvel at it and say how nice and compact you are. And then you do one simple value iteration, it becomes ugly and big. One more value iteration, it becomes even uglier and bigger. Eventually, it will become as big as the entire value table. I hope you understand this. You were not unhappy before because you were sunk already. Okay? Because you already started by assuming that the hypothesis distribution was provided in the extensional form. And when you update the extensional form hypothesis distribution, it can't become any bigger. However, in this case, rather than represent, and of course extensional form representation, sometimes you don't want to do extensional form representation even for discrete variables. For example, you might start with a noisier distribution or a Poisson distribution, even for a discrete variable. And if you started with that way, then there is no longer any guarantee that the posterior would be of the same form. If you start with a noisier, it doesn't have to be the case that the posterior would be noisier. If you start with a Poisson, there is no guarantee that the posterior is going to be a Poisson. Okay? So it's because you are used to better luxuries in life where you could represent the distribution more compactly, you needed to be sure that you can keep that luxury. Okay? The good thing about parameterized representation, essentially in that case, like in a Poisson distribution, you can represent all the values with just one parameter. You can represent the entire distribution with just one parameter. And the noisier distribution, you can represent 2 power n minus 1 numbers with just using n numbers. And so you are interested in keeping that advantage. In the value function in ADDs, you represented the entire value function using a small ADD, so when you change it, you still want to be a small ADD. You're no longer guaranteed normally, but that's the kind of thing that you're interested in. Okay, now, in this case, we are actually talking about continuous distributions. Now, one of the interesting things is for continuous distributions, you never actually ever write it in a tabular form, because it's impossible. This is why, in some sense, when you heard about statistics, you always heard of things like normal distribution, etc. For, if you thought of continuous quantities, you started with that side because there was no way of ever writing. If you have a continuous value function, you'll never write it as a tabular representation. Okay? So why didn't we care about this earlier? Because we already were using tabular representation and you can't do any worse. Here, you want to, let's say, represent p theta in some, compact form, okay, hopefully with few parameters. And if it's, let's say, it was a normal distribution, it would just need 2 parameters. And the question is, then when I update this normal distribution with the data using Bayes' rule, I'll get a new distribution. The question is, will that still be normal distribution? Okay, that depends on the distribution of the data itself. the distribution of how the data changes given the hypothesis. Okay, and when you have this property, since this property is rare, you actually make a big deal about it, and you say, if the prior is in a form such that after Bayesian update, you get the posterior such that this and this are of the same form. If they are the same form, then whatever the update you did here, whatever the distribution you used here. So notice that here, this is the hypothesis, and this is the data given the hypothesis. This is a distribution too. You multiply this distribution by this distribution, and you need to get a new distribution that should be in the same form as the original hypothesis distribution. If that happens, then I would say this and this are conjugate. This is called the likelihood, data given hypothesis. This is called the prior, just the hypothesis prior. If you multiply prior distribution with the likelihood, if you get a posterior which is in the same form as the prior, then you say these are conjugate distributions. If you can find conjugate distributions, then if you can somehow represent your prior knowledge as an instance of the conjugate distribution, then you can actually do Bayes learning without keep on increasing the number of parameters after each posterior update. You see what I'm saying? This is a huge deal. It's such a big deal that I think I have mentioned earlier that there is this whole area called Kalman filtering, for some of you know from robotics. And why is Kalman filtering interesting? Kalman filtering has this property that if you start with a normal distribution and you update your posterior using a conditional normal, you'll get a normal again. And since normal only requires two numbers, you can always figure out your current information about the distribution with just two numbers. It's not always the case that any arbitrary distribution can be compactly represented as two numbers. Basically, normal distribution is represented in terms of two numbers because you have two numbers and an equation behind you, an expression behind you for the Gaussian distribution. The good thing is that everything will be Gaussian. You start with a Gaussian and you have a Gaussian conditional, you'll always get a Gaussian. And that's the big deal about Kalman distribution, Kalman filtering. Okay? And so you will never have to keep increasing the number of parameters. And the same equivalent problem comes here in the Bayes learning, and the big thing that we care about is, can we find a distribution such that for the heads and tails problem, or things like heads and tails problem, when you multiply the prior by the likelihood, you will get a posterior which is in the same format. Now, think of what happens for heads and tails. If I do have, so if I assume, so I have a p theta, which is the prior, which tells me the prior over the theta values. Now, if theta is the value with which heads will come, then what's the probability of heads given theta? Just theta. So I need a distribution such that p theta times theta will be of the same form as p theta. That's what I want. Okay, it turns out that there are a family of distributions. Now, by the way, this particular distribution here is Bernoulli distribution. It's called Bernoulli distribution. Okay, because essentially it's telling you heads and tails, with heads comes with theta probability, tails comes with 1 minus theta probability. Okay, and the conjugate for the Bernoulli distribution turns out to be a distribution called beta distribution, which you may not have thought of if you haven't heard of distributions before. We'll talk a little bit about it, because beta distribution is just a distant cousin of Dirichlet distribution, which you probably heard too much about in reading LTE. And if you understand beta distribution, it's like understanding the simple case of Dirichlet distribution. And it's used exactly for the same reasons, except it's just used for a multinomial versus a binomial case. Here we have a binomial case. In general, you have a multinomial case. That means a variable can take not just two values, but k values. And then it takes the first value with theta 1 probability, second value with theta 2 probability, third value with theta 3 probability, and kth value with theta k probability, such that theta 1, etc., up to theta k equal to 1, sum of that equal to 1. And if you have a multinomial distribution, then the p theta, which will have the conjugacy property, turns out to be Dirichlet. So that's the foreshadowing. Okay? But let's understand why, what happens with beta first. And pretty much every little insight you get from beta distribution will carry over to Dirichlet. And beta can be easily visualized. Dirichlet is a multidimensional distribution, and so beyond 3 you can't even see what's going on. Okay, so beta distribution is of the following property, is form. Beta distribution has two hyperparameters A and B, okay, and it is a distribution of the quantity theta, and it basically says some constant times theta power A minus 1 times 1 minus theta power B minus 1. That's the distribution. And what should be that constant? The constant should be such that the sum, the integral, would be equal to 1. Because it's a distribution function, so the area under the curve must be equal to 1. And it turns out that the alpha is connected to the gamma function, which we'll talk a little bit, but it's not that important that you understand if you don't already know what gamma functions are. But there is a distribution like this. This is a family of distributions. Notice that based on what the values of A and B are, this distribution will have a different shape. Okay. But if you start with this distribution, suppose you were to express all your prior, so this is basically what I'm saying. So you have some prior belief, let's say, about what will happen in the world tomorrow. You need to express it in some language. I'm suggesting you express it in the beta distribution language. Okay? Now, it may well be that that's not the best fit. But if you find the closest beta distribution that sort of expresses your biases as to what is more likely versus less likely to happen tomorrow, then I have this computational advantage that I can do the updates very efficiently. Do you understand this? So in fact, you might know what your prior knowledge may not be an exact fit to any given beta distribution. Even though there are infinite number of beta distributions, that doesn't mean that your prior knowledge is equivalent to any one of them. But if you find one of the closest ones, like find some beta distribution that's sort of close to your prior knowledge, and stick with it, then as the reward for doing this, your life becomes infinitely simple, because you can then multiply this prior by Bernoulli likelihood, and you will get the same form prior, same form posterior. That's what I'm saying. So if you have, if you pick some beta distribution, and picking a beta distribution is picking the AB values. Okay? Now, if you pick a beta distribution, then updating it essentially. So suppose suppose the p theta is this, the prior distribution over the thetas. Now, prior distribution over theta is the same as prior distribution over hypothesis, because theta is your hypothesis. Okay. Now, the posterior p theta given the first data point happens to be head. Okay. That would be using Bayes' rule, some constant times p d1 equal to head given theta times p theta. This is the normalization constant from the Bayes rule. Okay, now notice this has a normalization constant, and this guy also has another constant, normalization constant. Now you multiply those constants, I'll get alpha dash here. I'll keep that as alpha dash right now. Times p d1 equal to head given theta is nothing but theta. Okay, right? Times, so theta times theta power a minus 1 times 1 minus theta power b minus 1. Right? And that looks like this form. Alpha dash times theta power a 1 minus theta power b minus 1. And I argue that is nothing but a beta distribution. You started with beta distribution with parameters a and b. You now get a beta distribution with parameters a plus 1 and b. If you were to write a beta distribution with parameters a plus 1 and b, that would look exactly like this. That's what I meant by saying starting with a beta distribution prior and doing a Bernoulli likelihood gives you back a beta distribution. Do you understand what I'm saying? Okay. This is the big deal about conjugacy. And so beta distributions are called conjugate distributions for Bernoulli distributions. Okay. And then for multinomial it's Dirichlet, and for normal it's normal itself or normal Wishart. There are different families of. For some standard families there are conjugate distributions which happen to have these nice properties. Okay. And then if you can somehow express your prior in those conjugate distributions, your life becomes simple. The reason I went over and over and over about this partly is I think many people don't quite understand, even those of you who may have heard of conjugate distributions before, there is no obvious reason why your prior knowledge should be fittable in a Procrustean bed of the beta distributions. Do you see what I'm saying? So for example, it's like push-pulling, right? I would say, do you think, and then I'll ask you only some questions, and you have to say yes, no, only to those questions. Maybe you know a lot more than those questions, and you want to express that. No, sorry, because I'm only going to ask you these questions because this way I can express it as a beta distribution. Okay? So the effect here, now here's the other interesting point. So think of, so beta AB is this. What would beta 1,1 look like? Beta 1,1 would look like
1.
Theta power 0 and 1 minus theta power 0. That's basically a uniform distribution. It's constant everywhere. If you started with beta 1,1 and you saw a head, according to this reasoning, you will get beta 1 plus 1 and 1. So you'll go from beta 1,1 to beta 2,1. That's a slightly different distribution. It's no longer uniform. Suppose you started with beta 1,1 and you saw A heads and B tails. Then the posterior would be beta AB. I'm sorry, no. Beta 1,1 and you saw A minus 1 heads and B minus 1 tails. Then the posterior would be beta AB. You see what I'm saying? So what this actually means is another interesting thing that's happening here. If you go with this conjugate distribution, your prior knowledge is completely specifiable in terms of some hallucinated samples you have seen before you saw the very first sample. Do you see what I'm saying? So the guy who starts with beta AB prior is different from beta 1,1 prior in only as much as beta 1,1 prior, when he sees the first head, he thinks it's the first head they ever saw. Beta AB prior guy thinks it is the A plus 1 head, because they've already seen A virtual heads and B virtual tails. Do you see what I'm saying? So this is actually a very useful thing to realize that having a prior, in this case, is like having seen some number of virtual examples, or acting as if you have seen some number of virtual examples. And those of you who may have done anything like Laplace smoothing in naive-Bayes classifiers, for example, you would see that in naive-Bayes classifiers, to avoid zeros, you would add 1 to the numerator rather than the denominator. That's like seeing virtual examples. Okay, so it's all these nice connections. This is not a general property. It just happens to be true. If you take beta as the conjugate distribution of Bernoulli, then the effect of starting with beta AB is the same as the effect of starting with beta 1,1 and seeing A minus 1 heads and B minus 1 tails. After that, you will be the same as your friend. And this also tells you that nobody is ever going to have a prior that will not be affected by the data. They're always willing to change their prior. The procedure ultimately changes. Okay? Now the beta distribution. So this is the reason I want to show this to you is I want to tell you what do you lose? What do you lose in expressing your prior knowledge as a beta distribution? I told you that not every prior knowledge can be expressible in beta distribution. But you do this because it will give you a mathematical advantage. It's like looking under the light for the keys that are lost. Not because they are lost under the light, but because that's where the light is. Okay? So you picked conjugate distribution not because that's the best way to represent, best fit for your prior knowledge, but because that is the family that has the good property. Okay? So it's a good family, it turns out. And basically this is the exact definition of the beta distribution, except written in terms of alpha and beta. It's kind of bad. Beta distribution instead of A and B, I wrote alpha and beta here. Where the hyperparameters are alpha and beta. Okay, this is a Wikipedia page, which they have it in alpha beta, so I just copied it. Okay, so again, it's x power alpha minus 1, 1 minus x power beta minus 1, divided by this integral. Because whatever this integral is, you need to essentially make sure that when you add all of this up, then this integral, you get the area to be 1. And it turns out, and if you happen to remember your calculus enough, which you can show that this integral can be written in terms of gamma functions. And gamma functions, for those of you who haven't heard about them in recent years, are continuous version of factorials. Okay, so gamma x, if x is an integer, gamma x is x minus 1 factorial. Okay, so let me show you this. So basically, this is how gamma function looks. Normally, we only know gamma function for the integer values. 2 4 and so on. And basically, gamma function is one of the many functions that you can interpolate between the points, such that it will have the same value as the factorial at the integer values. Okay, and we'll have some other values in between. And it is one of the well-behaved functions. It's like reasonably continuous in the regions and so on. There's like beautiful amount of math about gamma functions. If you haven't heard about it, you can go and read lots and lots about it. Okay, and a gamma function kind of looks like this. Of course, from 2 onwards, it just keeps going up to 1, and then from here to here, it comes down, and then that's how it looks. At every negative integer, essentially, it's undefined. Okay, fine. And this is a well-known function. You may not know it, but other people know it. And there are tables which will take gamma x equal to and then give the value for it. So as far as you are concerned, this is an actual constant. You can say gamma 2.3. So for example, gamma half turns out to be what? Does anybody know?
I think it's square root of pi.
Square root of pi. So that guy obviously knows gamma functions. Gamma half turns out to be equal to square root of pi. That's one of those cute properties for gamma functions. Okay. So for every value of gamma and for every value of x, gamma has a value. And if you want gamma half, you can ask him. If you want some other number, there is a table somewhere which will tell you what the values are. Right? And so that's basically the gamma-based constant. And so you will see in the LDA function, you will see huge number of gammas. The reason is Dirichlet is nothing but beta distribution for multiple dimensions, not 2 dimensions but k dimensions. So Dirichlet is nothing but beta for k dimensions. And so here you have gamma of alpha plus beta by gamma alpha and gamma beta. For the Dirichlet equivalent, it will be gamma of alpha 1 plus alpha 2, etc. up to alpha k by gamma of alpha 1, gamma of alpha 2, gamma of alpha 3, etc. up to gamma of alpha k. It's just a function. You can call this a table and it'll tell you what the number is. Okay, so that's the gamma function. Now let's just look at what the shape of the distribution looks like. Remember, the beta function basically is going to be a distribution over x taking values between 0 and 1. Because x is a probability, and the probability can only take values between 0 and 1. And we already knew before we came that beta 1, the alpha equal to 1, beta equal to 1, it's not shown here, but that's just uniform. because alpha equal to 1, beta equal to 1, these two things become 0. The exponents become 0, and so you just have a constant. So it's a uniform probability. It's the uniform probability such that it will actually, the area of that rectangle is equal to 1. Okay. Now, this shows you the different other gamma values, alpha, beta values. Alpha, beta here is the same as A and B there. Okay. So if alpha equal to beta equal to, alpha equal to this one, let's look at this. Alpha equal to 2, beta equal to 2. Alpha equal to 1, beta equal to 1, it's just a uniform distribution. Alpha equal to 2, beta equal to 2, a nice happy car with a single mode. Now if you do alpha equal to 3, beta equal to 3, it would be a car which is even more peaked but in the same area. Alpha equal to 15, beta equal to 15, it will be kind of okay. So that does that tell you? It tells you that the peakedness of this distribution. Now you might say, why the heck do I care about beta distributions? I didn't sign up for this course to know about beta distributions. Well, beta distributions is the language in which you're going to put your prejudices. Prior knowledge is prejudices. Okay, you better know the language in which you're going to write your prejudices. And that way you'll know whether or not it's a good enough language for your prior knowledge. Okay. So first one idea here is alpha plus beta gives how peaked the distribution is. Okay. Now since the alpha and beta are two different numbers, I don't need to always have them equal. If they're equal, that's called a symmetric beta prior. Equivalently, for the Dirichlet, symmetric Dirichlet prior of 3 dimensions will be alpha 3, alpha 1, 3, beta 1, 3, alpha 1, 3, alpha 2, 3, alpha 3, 3. And Dirichlet would now be in the 3 dimensions. It'll be, here it's like here is a cross section of the Dirichlet. So in the actual Dirichlet of 2, 2, 2 would look like a nice little cup like that. A Dirichlet of 15, 15, 15 would be a kind of a much more like a sharp cup. A Dirichlet of 5, 5, 5, 5, 5 will be, if you could show it to me, I would have been really happy. And I would have taken the same drug you were taking, because then you are able to see 4 dimensions. Okay, right? But 4-dimensional Dirichlets exist. It's just I can't show nice, things. You can only show the cross sections of the 4-dimensional Dirichlets. This is why it's very important to get your intuitions right in the second 2 dimensions and 3 dimensions, so that you know what happens in the n dimensions. Although intuitions from lower dimensions are pretty bad for high dimensions in general. Okay, but anyway. That's for alpha 2 beta 2. Now alpha 2 beta 5, that's this guy. And it looks like this. Okay? And now, how about this alpha 2 beta 5? Then this is alpha 5 beta 1, and it looks like this. And the way to understand it is the alpha plus beta tells you how peaked the distribution is. If alpha and beta are equal, then it's sort of nice like a cup with one little difference, and we'll talk about it in a minute. As long as alpha plus beta are greater than 1, then if alpha is greater than beta, it looks like a nice cup, an inverted cup. Okay? If alpha is greater than beta, then the peak occurs closer to 1. If beta is greater than alpha, then the peak occurs closer to 0. It becomes a skewed distribution. Do you see what I'm saying? Okay, so this gives you an idea, right? I mean, if you think that whatever it is that's going to happen, this particular coin that I'm tossing, your prior knowledge says it's more likely to be heads than tails. If that's what your prior knowledge says, then what would you do? So heads probability has to be higher, so essentially make alpha be higher than beta. Alpha is the head, count, essentially. Act as if you've seen already some heads before they show the first thing. Okay? And then the last thing, of course, is what happens if you have alpha equal to beta equal to 0.5. Alpha equal to beta equal to 0.5, this is this curve. That one essentially puts all the probability mass on the sides. And so the mode now is not in the middle but on the sides. All you care about is that the area under these curves is equal to 1, and it is true that the area under those curves is equal to 1. But there are many different ways of writing these curves. Now, my question is are these the only curves you can write such that the area under the curve is equal to 1? No. Can you tell me a curve that you can write which doesn't look like any of these curves?
Flat line. Straight line.
Straight line actually is taken care of because alpha equal to beta equal to 1, that's uniform distribution, that's straight line. Slope, yeah. But you can sort of, if you have a slope, then you need to kind of take something like this and say this is my thing. The one that certainly won't hold is bimodal. If in doubt, in statistics, say multimodal. That's always the bad thing. Okay. Remember, normal distribution is happy single mode. Okay. Now, actually, you can say this is sort of bimodal distribution. But multimodal distributions can't be captured by beta distribution. So that means if you somehow think that this coin I'm about to toss is either 0.3 heads and 0.7 tails, or 0.7 heads or 0.3 tails, and everything else is less likely. Do you understand what I'm saying? Then you are no longer able to express that prior knowledge exactly by picking one of these infinite number of beta distributions. That's the price you pay for requiring conjugacy. Okay? Now, any questions on this?
This second line, how it comes from the first one?
This one to this one. Do the integration.
Second to first.
No, this from here to here.
Yeah.
This is just basically, this is the expression for the area under the curve. Integration can be used to find the area under the curve, or the area under the curve, has to be, the total area under the curve has to be 1, so you just divide. Okay. Fine. So this is the gamma function itself, and as I said, it's a continuous version of, the factorial function. And the conjugate prior, a prior distribution family, is considered a conjugate prior for a likelihood function family P1 if starting with the hypothesis prior of this form and doing the likelihood update, you will still be in the same family but with the different parameters. That's a very huge improvement. Because otherwise you will start having, in general, when for example, Kalman filtering fails exactly when there are multimodal prior distributions. And Kalman filtering, suppose it turns out that the enemy aircraft is either here or here, and you just try to do Kalman filtering, you will start tracking a non-existent aircraft which is sort of in the middle, which is neither here nor there. Okay, and if you do the particle filtering, then particle filtering, basically the whole point of particle filtering, again this is for the couple of you who are actually from robotics here. The whole point of particle filtering is you start with any arbitrary distribution and then just keep a representation of it in terms of its samples. Okay? So that's for conjugacy. As I said, beta distributions are conjugate for Bernoulli, Dirichlet are conjugate for multinomial. So really, Dirichlet is nothing but beta for k dimensions, k greater than 2. That's it. So you know Dirichlet now. And if somebody tells you you don't know, then you tell them you know. And you certainly can tell what happens. Just from this picture, you can tell how Dirichlet distribution for 3 dimensions looks. It will have three parameters, alpha 1, alpha 2, alpha 3. And if they are all equal and greater than 1, then it will be sort of a cup, 3-dimensional cup. And if they're all equal and the sum is less than 1, then it will be more like this. So it will be like a cup, downside. I mean, the normal curve. The other one is this kind of curve. Okay? And then otherwise we get all sorts of funny curves, with the bumps in the sides of the sides. Now, one other thing that's a big deal if you started looking at LDA paper is notice that here the distribution is defined in 2 dimensions only from 0 to 1. Because the parameter can only be taking values between 0 and 1. In fact, actually, for Bernoulli distribution, there are 2 parameters, theta 1 and theta 2, except theta 1 plus theta 2 equal to 1. And theta 1 as well as theta 2 must be greater than 0, greater than or equal to 0, right? And because of which, essentially, if you just take, one dimension, if you just consider theta 1, and that only travel between 0 and 1, the other guy will be traveling between 1 and 0 at the same time. Okay, now if you have 3 dimensions, then you have 2 free parameters. Okay, so in 3 dimensions, in the 3-dimensional space, Dirichlet has to be defined only over those points, only over those 3-dimensional points, such that their coordinates are all greater than or equal to 0, less than or equal to 1, and they sum to 1. So in 3 dimensions, basically you are looking for the space where x1 plus x2 plus x3 equal to 1, and x1 greater than or equal to 0, x2 greater than, x1 is between 0 and 1, x2 is between 0 and 1, x3 is between 0 and 1. It turns out that thing that you're looking for then is the simplex. Okay, it's called a simplex. It's basically a triangular area over which all the points, all the coordinates of the points when summed will be equal to 1. And so that's why Dirichlet, just as beta is defined only between 0 and 1, 3-dimensional Dirichlet distribution will be defined over a triangular, 2-dimensional triangular area. Okay? And over this 2-dimensional triangular area, you have 3-dimensional upside-down cups and downside-up cups, and funny-looking cups and other funny-looking cups. Those are the distributions. And 4 dimensions, you can't describe these things. Okay? Now, we have been talking about heads and tails and Bernoullis and Bayes learning, etc. I want to talk about Bayes networks, which is what we were interested in originally, right? So what did the Bayes network look like when you did not have to take prior into account and when you did have to take prior into account? Again, one more thing here. Everything I say here will be useful in understanding LDA too. Okay? So when you don't have prior into account, then essentially the only parameter is the face of the, whether it's coming heads or not. If it comes heads, then it didn't come tails and vice versa. Okay? So the only random variable is heads. Right? And then it is basically this is the Bayes network. The Bayes network has just a single node. That's heads. Now if I just give you a Bayes network with a single node, I need to give a prior over it, given all its parents. This guy has no parents. So I just need to give a prior just on theta, just on h, just on h. And that is the Bernoulli distribution with some theta. In MLE, we assumed we didn't know theta, what theta is, and we tried to find a value for theta such that the observed data's likelihood is maximized. That's what you did. Okay? Now, if you have this whole beta distribution which actually winds up changing the theta value for the heads random variable, then your Bayes network looks more like this. So there is an extra variable, theta, whose prior, capital theta, whose prior is beta. And it picks its value from that beta, and this guy basically gets that value as its Bernoulli parameter. Now notice that this is the first data point. The second data point, the second time I'm going to toss heads again, I'm essentially sampling. So again, Bayes network models also are called generative models. And what does generative model mean? Generative model means that I can generate the data from scratch. How do I generate the data here? I'll start from here, sample the beta distribution to get a theta value, and then use that theta value to toss the coin. And if it comes heads, I'll say heads. If it comes tails, I'll say tails. Now the second time I'm picking, again doing this tossing, then I again go back here, resample the beta distribution to get a new theta value, and then toss it again. Do you see what I'm saying? Okay, so this is how it looks like. Okay, so you have theta changes each data point. Each data point itself is a random variable. And they are all independent of each other given the theta. It's still IID. There is a picture like this I drew in the very beginning of Bayes learning. Okay, and that's what I'm drawing here again. Now the interesting thing, of course, is so the H, so these are all the data points, D1, D2, D3, D4, etc. And then as you start with theta prior and you see a head, then you now have this Bayes network. Just this guy and this guy. Based on this, I can compute the posterior of theta. And if I see a tail, I now have these two nodes and this guy. So now I recompute the posterior of theta. And as I keep doing this, I keep getting different beta distributions. You see what I'm saying? Now, the interesting thing, of course, is as the new data is coming, if I'm about to predict the next data point, then how I would do it is based on all these data points, I know what my posterior is. I use that posterior to predict the next data point. Not the original prior, but the posterior. Posterior would be dependent both on the prior and the data you have seen, which is exactly the way it should be. Okay, 2 points here. One is suppose this kind of shows a picture of how, let's say, suppose unbeknownst to you, it turns out that this is a coin which comes 75% heads and 25% tails. That's the way it is. I just know it. You don't know this. Okay. So as you keep looking at the data, after some amount of time, let's say you saw 3 heads and 1 tail. Remember, you start with uniform, so you had a nice little uniform beta prior. Then after seeing 3 heads and 1 tail, the posterior would look like this. Okay, and so in some sense, the mode of it is that essentially you're going to be, so the mode of it is some more here. Okay, now after you see 6 heads and 2 tails, which is nothing but 3 heads and 1 tail times 2, it becomes more peaked. Okay, so it looks like this. And after you see 30 heads and 10 tails, it looks like this. This is what the beta distribution actually looks like. And this is what the posterior will compute, because you remember, if you see 30 and 10, you will get, if you started with beta 1, 1, you will get beta 31, 11 after posterior updates, after 40 posterior updates. And that would look like this. And so, in essence, this reasonably is capturing your intuition that the data is making you realize that you are, by about here, you already know that it's kind of biased coin. But by this time, it's, biased with the mean being 0.75 and the variance is becoming smaller and smaller. So you're pretty fairly confident. This is another beautiful point about Bayesian learning. In general, when you learn something from the data, people would like to know how serious are you, how confident are you, and how confident are you in your prediction. So normally the prediction would be the mean, and then you need to give the variance, plus or minus. For Bayes learning, it comes as free, because you are reasoning with distributions. Yes?
The y is a probability.
Which one?
The
Yes.
red. Then
No. This is the probability that theta equal to theta.
So,
and this is the density function. Remember, these are continuous values. The density function should sum up. The area has to be 1. This is not discrete function. If it's a discrete function, no single value can be greater than 1. In fact, if you have a so this is again, this sort of tells me that you are a computer science guy, right? Because you've forgotten continuous functions. You know, in a continuous function, what happens if you know for sure, that it's 0.75 is theta, and no variance? How does that function look? It would have to look like that. I mean, if I do taller, I go even taller. It will be the delta, Kronecker delta function. It has infinity as the value at 0.75, but it has no width. So integral happens to be 1. And we have all of you in computer science have forgotten this stuff, because you've done calculus, but you never had to touch it again. Okay? But that's the thing. It's a good point. It's points, it's 6, but that doesn't mean anything, because all you care about is the area. If I make it thinner and thinner, this can become bigger and bigger. Okay? The other thing related to this point is, notice that this is a reasonably cumbersome notation right now. As the data increases, the network becomes bigger and bigger. So this would be the network for the 1 data, this would be the network for 2 data points, this